Sure, hold on.
Okay, so first part, this is sort of a review. We talked about yesterday. All the inference for means is built around the sampling distribution model. So this is a little quiz. Do you remember what the center is of the sampling distribution model for means?
X-bar.
Close.
Is it like U?
The mean. Here, I'll give you it. I'll start it. You write it like this. So this is saying the mean of all the sample means, the mean of all the means is
The mean of the
Oh, just
the population.
is the mean.
Yeah.
The mean of all the means is the mean.
That's not.
No, not at all. This symbol is really saying the sampling distribution mean is equal to, what does this symbol mean?
Population.
That's confusing. Say, what does this mean? It means the mean. Okay. Right, this is the population mean. And then the spread is always standard deviation. So this is easier. Standard deviation of all the means is standard deviation
Over N.
Standard deviation over radical N. It's okay. You weren't here yesterday. You shouldn't have known that. Good. Now, if you don't know the population mean and standard deviation, then you can estimate with the sample. So sometimes you'll estimate with the sample mean. So this is all just getting the symbols straight. So you estimate the sample mean, you can estimate this with the sample standard deviation. If you don't know what it is. Do you remember the formula for sample standard deviation?
Isn't it P1 times, P hat times 1?
Oh, so P is proportion.
You have.
I remember.
Sample standard deviation is.
That's what I was going to guess next.
That was going to be your next guess. Okay, before we go on to the conditions.
So SX is sample standard deviation.
We are looking at the sampling distribution model. Now yesterday I said the sampling distribution model, when you have really big sample sizes, is like the normal model. But this doesn't say normal model. What does it say? T model. We have never dealt with the T model. Use what's called the T model when you estimate the population and standard deviation and mean. And it has what's called degrees of freedom. It's n-1, that's another complicated formula. What is n? Sample size. So if your sample size was 25, then you would be using a T model with 24 degrees of freedom. Okay, turn the page. Before we go on, we're going to talk about the T model a little bit. I'm going to have you read something in a couple days. It's a little bit interesting about why you use the T model instead of the normal model. But for now, just know we're going to see what it's like. It's very, very similar to the normal model. So, can you see your graph? Okay. It says the properties of the T distribution or T model. It's symmetric about 0, just like the normal model. It's symmetric, it's unimodal, it says it's bell-shaped, very similar to the normal model. However, if you look over here at the degrees of freedom, it goes 1, 2, 5, 20, and then the last thing says I and F. That's what? Infinity. When your degrees of freedom is infinity, that is the normal model. I would definitely write that down. So, the darkest line on this graph, I'm going to try my tracing skills. The darkest line, that's the normal model. That's pretty good, right? Okay, so look at the normal model compared to the other models that are all drawn in. What happens in the middle here? Yeah, the other models are lower than the normal model. But look at the ends. No difference? Yeah, see how they get a little bit higher? So this is what it means when it says they're more spread out than the normal model. It's heavier tails. So this very first line, that's degrees of freedom 1. And then the next one is degrees of freedom 2. And then 5 and then 20. In the center, it's lower, but on the outside, it's 1, 2, 5, 20, etc. So there's more data in the tails when you have less degrees of freedom. So again, there's more in the tails. Do you see how that's thicker for the highest line, which is the lowest degrees of freedom? So there's more data in the tails when there's less degrees of freedom.
Have you explained what degree freedom is?
Well, I don't really remember what it means. It's just n minus 1. So if there's 100 in your sample size, the degrees of freedom is 99. I do kind of know what it means, but you don't need to know. Okay, it says as the degrees of freedom increase, the t-distribution is more like the normal distribution. So here's kind of what you need to know. Here's the kind of questions you'll usually see that relate to this. If I have two distributions, one of them n is 50, and the other one n is 30. Okay. And I'll keep my best. So there they are, graphed together. Those are both T models, or T distributions. One with the n of 50, one with the n of 30. So what is the degrees of freedom?
49 and 49.
It's 49, and this one, the degrees of freedom is 29. Okay, which one is which? Embarrassing.
What did they do?
Hannah, put your phone up.
You don't have to say my name. Not everyone's gonna know who it is.
It'll be okay.
It's not communicating.
It is okay.
Would the blue one be?
That's why I don't talk on these.
Which one's which?
The blue is the first one.
The blue is 50. Right.
Is that
And then the
less?
green is. Right. So it gets higher and smaller tails the bigger the N is. Make sense? Leave it here.
Wait, what did you just say? Bigger the tails?
The bigger the N, or the degrees of freedom, it has smaller tails. Like the blue, this one is the blue. That one is. See? Okay. Got it. Okay, quickly, we'll go to the conditions. There are still conditions you have to check. So sad. Who remembers the first condition for proportions?
We're gonna do that. Representative and bias.
Yes. So is it similar to this condition? Yes. Second condition for proportions?
Less than 10%.
Less than 10%. Same thing. Go back to the front page. And the last one, so with proportions, that's where you had to do the n times the p. When you did that, some of you realize this, I think, you were seeing if your sample was large enough to have at least 10 successes and at least 10 failures. So we're still checking the same condition, but there's a different way of checking it. It either has to be really large, but you don't have to multiply times anything, it just has to be bigger than, we'll say, 30. So if you have a sample that's bigger than 30, you can say it's large enough, and that's checking your condition.
Will
But,
they typically tell us what that is?
yes, it's very rarely bigger than 30. That would be too easy. So if it's not bigger than 30, it doesn't mean the condition's not met, but it means it has to instead be nearly normal. Which nearly normal means it needs to be unimodal and symmetric. So sometimes you'll be given a graph, but what if you're not? How do you know if something's unimodal and symmetric?
And the mean and median close.
That is good, but that doesn't tell unimodal. That tells symmetric. Because it could be perfectly bimodal. You're going to have to make a histogram. So it'll be a good review. Something we haven't done in a long time. I'm not doing it today.
Do we have to write the histogram to prove ourselves, or is that something we can
Sketch it.
just,
Mm,
like on the AP test, is that part of it?
yes. Yeah, probably. Okay. We're not going to check any conditions today, though. Is that okay?
Yes.
We are going to go. Okay, let's talk a little bit about confidence interval. So, confidence intervals. We used to do a 1 proportion C interval. Now we're doing a 1 sample T interval. On your calculator, if you want to check real quick, I think we decided first hour that it just says T interval. I didn't look it up. You might see. So don't do OT test for interval. It's underneath 1 proportion Z test. Z interval. Is it just a T interval?
Yeah.
Okay, so it doesn't say 1 sample, but that's the same thing. It's just a T interval. So I can't trick you this time and make you do it by hand. Everybody knows you can use the calculator, so I might as well say it from the beginning. But just so you remember how a confidence interval is set up.
So are we gonna have a T level?
Yes. Oh, not a T level.
I mean a T score?
Yes.
Are we gonna have a T score?
Yes. Any more questions? Ask about it.
Oh, are we gonna have a T value?
Yes. No, you're not. I lied. Just got to have the same.
But a T hat.
No. Okay, this right here is the formula for all confidence intervals. It's always a statistic, plus or minus what's called a critical value, times the standard deviation. Statistic means it comes from a sample. So, when you're finding a confidence interval for means, the statistic is sample mean. Good try. I tried to help you out with this. You got the wrong word. The critical value, anyone remember what that was when we did proportions? That was the Z star. So now we're doing a T star with n minus 1 degrees of freedom. Because not all T stars are the same. I know. This is another language. And then what's the standard deviation? Look up at the top of your paper.
That big.
Yes. And I'm writing SX because you don't usually know the population. Okay, so if you'd like to continue doing it by hand, there's the official formula. Which part of that is the margin of error?
The part after the plus or minus.
So most of the time you use your calculator. Alright. We're going to do one kind of interpretation, but first I need to show you where the T star comes from. This is a table. You have an orange table. Do you want to get it out and look at it? You do. Nice little break. Stretch. Look for your orange table.
It's pretty hard to find.
I know. It blends in with all your other papers. Hmm? Yay. Okay, find table B, the T distribution critical value. It says critical values in case you forgot what the critical value is. Okay, if you wrote on this when we used it before, down at the very bottom, I just copied a little bit of it. It has the infinity row. And what did you write out to the side? Or did I have you do that?
Z star.
Yeah, that's the Z star. So when it's infinity, just like right here, I said infinity, that means it's normal. And that's when we found the Z star. So that last row is Z star. The rest of that table are all T stars. Everything in that table. And you see DF is the degrees of freedom. So since the model changes based on the degrees of freedom, so does the T star. Remember that has to do with the standard deviations. The tails are different, so are the standard deviations. Okay, I'm showing you this, but it's not. Let's say that we have degrees of freedom of 12. And I said, let's find a 90% confidence interval. What would the T star be? First of all, what would the degree, well, I just told you, degrees of freedom are 12. It's 12. So here's 12. And then at the bottom it says 90%. Is it this one right here?
Did you say 90 or 95?
Okay, on this it doesn't matter because down at the bottom it says confidence level. You just go with that. Good thinking, but you don't have to make that complicated. Okay, so if the n is 8 and we have a 95% confidence level, what would that be?
2.306.
95%. Now, if the, watch, I changed it on you. The n is 8, so what's the degrees of freedom? 7. Oh, is this one? I don't, I can't see with it. I think you're right, 2.365.
How come then we did that, the other one?
Because this is degrees of freedom, and then this one was n.
Okay.
So degrees of freedom, remember, is n minus 1. Okay, so what if you had to find a 90% confidence level, and the degrees of freedom is 55? On this information, you need a bigger table. So after, what does it do? After 30, it just starts skipping around. So like if it said find the T star for 55, then look at the one for 50, look at the one for 60. They're very, very close. They're like 1,000 off, maybe more or less than that. So just estimate what would be in between those two.
Is there a way to do this?
Yes, but it's complicated. It's not super complicated. This is easier. And you don't have to do it that often. Most of the time, you're going to use your calculator, I think, when you do a conference. Okay, we're going to do one example today. And it's just writing some interpretations. So, skip around, go to example 1. So you have time, extra time tomorrow. Okay, so this problem says a medical researcher measured the pulse rate of selected adults and found the following student-based confidence interval. So it gives you the interval. You don't have to do anything. There it is. So it just says explain what this means. So let's just review. Going back, how do you explain that? There we go. Remember this? We are 95% confident that. Okay, what are we estimating? Yes, and it's really important that you use the word mean because that's what we're estimating the population mean. So we are 95% confident that the mean or the average pulse rate for adults, mean, it's important, is between, and then you just tell what it is. please, when you're given a problem like that, do not write out all 6 decimal places. Well, I guess not. Do you want to? Okay, then do it. Okay, anyone remember how to find the margin of error when you don't know what n is, you don't know what t star is, you don't even know what the estimate was?
Find the middle.
Yes. Remember, confidence interval, you start with the estimate is in the middle, then it goes to the right, that's the margin of error, and then it goes to the left, the margin of error. So this one goes from 70.9 to 74.5. The margin of error is just half of that distance. Okay, so find the distance from 70.9 to 74.5. And then we only want half of that. So divide by 2.
1.8.
What, 1.8? It's really just making sure you know what margin of error is. Okay, according to doctors, I love how specific this question is. According to doctors, the average pulse rate of adults 72 beats per minute. Is this supported by the confidence interval? So doctors say that adults should have a pulse rate of 72. Is that what our confidence interval suggests?
Yes.
Yes. Why? Or how do we know? Yeah, it's just inside the interval. Yes, 72 is in the interval. So that's what the interval is doing. Remember, it's estimating the mean. In this case, it's estimating the mean pulse rate, somewhere between those two numbers. So 72 somewhere between supports that. Any questions so far? This is confusing for you. Okay, good. If the researcher had calculated 99% confidence interval, would the margin of error be larger or smaller? You remember what happens if you increase the confidence level? Confidence level means we're going to be more confident that we get the right estimate. Well, we are going to be more confident that we capture the right estimate. That means our interval is going to be larger. And the interval and the margin of error would be larger too. So the margin of error is saying the interval's larger, we have a better guarantee. Now we're 99% confident that the right answer is somewhere in there, but the margin of us making a mistake is a lot larger. Not really the margin of making a mistake, it's not like the margin of error, but there's just a lot of room. It's not as accurate. Okay, I didn't put E on here, so what's E say?
This confidence interval was created with a sample of 20 adults. If the pulse rates of a sample of 50 adults had been collected instead, and a 95% interval calculated, how would the sampling distribution model change?
Okay, so they had 20 and now they have 50 in their sample. This is just asking about the model. They had 20 in their sample and now they have 50 in their sample. How would the sampling distribution model change?
Would it be more normal?
It'd be more normal, that's all you have to say. More like the normal model.